Ladies and gentlemen, good afternoon. I'm deeply thankful to our conference organizers, to talented audience for this opportunity. I'm Abdullah Paraja, a student at Diponegoro University, specializing in forex trading with machine learning. Today, I'm excited to share my research on topic of optimize advantage actor critic to maximize prediction in forex trading. Advancement in technology have made forex trading more accessible online. Forex trading face execution challenge to predict the optimal execution price, such as latency due to complex model during market volatility and real-time data processing. Lastly, computational costs should be considered to avoid impacting profitability. Reinforcement learning is a machine learning type where an agent learns decision making through interaction with an environment, taking action to reach a goal. It learns from rewards or penalties to develop a policy that maximizes cumulative reward. Since reinforcement learning has the ability to search for unmapped condition, it is suitable for solving problems in the highly volatile forex market. There are several approaches to solving reinforcement learning problem, including model-free based reinforcement learning and model-based reinforcement learning. We use a model-free ensembling, Q-learning, and policy gradients. Model-free reinforcement learning is a method where an agent learns to make decisions based solely on its past experience and interaction with the environment, without creating a model of the environment. There are two main subcategories of model-free reinforcement learning: value-based method, policy-based method, and in between is the advantage actor critic. Q-learning is a popular algorithm in reinforcement learning where an agent learns to make decisions by interacting with an environment. The goal is to learn a policy, which is a mapping from states to action that maximizes the expected cumulative reward. Q-learning uses a tabular approach where the value of each state action pair is stored in a table called the Q-table. The Q-table is updated iteratively using a simple update rule which helps the agent to learn the optimal policy over time. However, this tabular approach is impractical for many real-world problems for several reasons. One, high-dimensional state space. Two, generalizations. The tabular method enables to recognize similarities between situations. It's slowing down and reducing learning efficiency. Three, continuity. For situations with infinite possible state or action, using a table for tracking is impractical due to the need for unlimited slots. This is where deep learning comes into play. Deep learning can handle high-dimensional data, generalize from the training data to unseen data, and work with continuous space, which make it a good match in reinforcement learning problems. In deep Q-learning, instead of maintaining table, we use a deep neural network to approximate the Q value. Given a state, the Q network produces the Q value for all possible action. The agent then selects the action with the highest Q value. The policy base is a mapping from state to action. It defines the behavior of the agent, determining which action to take in a given state. The goal is to find an optimal policy that maximizes the cumulative reward obtained over time. Policy-based methods are like a new video game player learning how to play. They don't know the rules at first, so they try different strategies. Every time a game is learning experience, over time they get better, but it takes a lot of tries and time. This makes learning slower and can also require more computational resources, which could be a disadvantage in some cases. The gradients indicate the direction in which the parameters should be adjusted to improve the policy performance. By iteratively updating the policy parameter in this direction, the policy gradually improves over time. One advantage of policy gradient method is that they can handle continuous action space where the action space is not limited to a discrete set of choices. They also provide a way to explicitly model stochastic policies, which can be useful in situations where exploration is necessary to find the optimal policy. Actor critic method is like having two players in a team. The actor is the player who performs action such as move in the game. The critic is the player who watches and gives advice on how the actor plays. The actor acts and the critic gives feedback on whether the action is good or bad. With the help of the critic, the actor learns from his mistakes and gets better at the game. They work together to get the high score. In the advantage actor critic method, instead of using the raw value function, the advantage actor critic uses the advantage function. The advantage function measures the relative value of an action compared to average value of all action in that state. The advantage actor critic algorithm will work as follows. The actor agent decides what action to take based on the current state, like deciding whether to buy or sell in a forex market. This action affects the environment, change the state like change the forex prices. The environment then gives back a reward and the new state based on the action. The critic agent estimates the value or future rewards of the new states and provide feedback to the actor on how good the action was. The actor uses this feedback to improve its policy or way of choosing action, aiming to increase its total reward over time. So the advantage here is that both the actor, which decides the action, and the critic, who evaluates the action, work together to achieve the best possible outcome. We experimented by applying it to the forex market for the Euro USD currency. The platform we used was MetaTrader 5 or MT5, a highly reputed and widely utilized platform among forex traders, as it offers advanced charting tool, automated trading capabilities, and providing access to comprehensive historical database spanning the previous 15 years. The raw data used include the time series data such as opening, high, low, and closing price for a particular currency, as well as other market indicators such as tick volume. We download historical price data in 5 years from 2018 to 2022, reach more than 8,000 rows of data. To address market non-stationary and ensure model robustness, we use a split dataset approach. We divided our historical data into training, validation, and testing data. Training data was used to train our model and enable pattern recognition and learning. The validation data act as a checkpoint, allowing us to optimize our model parameters and prevent overfitting. Finally, the untouched testing data was used to access the final model's predictive power in a real-world scenario, providing valuable insight into the potential effectiveness in live trading. The agents learn to predict the best action based on the current market state and potential reward. Training involves repeating the learning process for 1,000 steps per episode using 4 years of data, taking around 6 hours per episode. Its duration may vary in other devices. This enables the agent to learn policies, cumulative reward, and observe the progression of total reward. The agent was put through a rigorous retesting process using EuroUSD historical testing data, which was specifically chosen because it was not part of the data set used during the training phase. This separation of different data ensured an unbiased evaluation of the model predictive capacity and adaptability to unseen market conditions. We focus on specific time frame for backtesting, the 4-hour candlestick interval from September 2022 to December 2022. This particular period was chosen for its current relevance and potential to test the algorithm's performance under contemporary market dynamics. The top graph is the test result after repeating the test for the 10th episode, showing that there has been a gradual gain. The bottom graph is the test result after repeating the test for the 15th episode. The profit is increasing but still not effective because there are too many negative results. After the 35 turning episodes show significant improvement with the number of trades becoming less, which is more effective as negative trades can be avoided. With reduced negative trades will increase the profit. Evaluation of the measured metric result shows, as in cumulative return that is used to determine the total return of the investment, it increased from 29 to 112. It exceeds the initial deposit. Similarly, the Sharpe ratio showed a significant increase after the 15th episode and only slightly improved thereafter. The Sharpe ratio measures the average return earned above the total risk. A higher Sharpe ratio indicates superior returns compared to the risk taken to achieve them. For average holding period return also get better than before. The holding period is the length of time an investment is held. As for maximum drawdown is used to measure the level of loss of asset value during a certain period. The closer to zero, the better. The maximum drawdown result in the 10th episode are still high, which is 36%, and in the 15th episode it has decreased to 24%, which a large number of transactions. In the 35 episode maximum drawdown become 4.48%. This is better because it is below 5%. We successfully developed an MKL5 based actor critic algorithm and conducted comprehensive training and testing using real historical market data. The promising result demonstrate the profit generating potential of our model. Establishing it is a strong foundation for a future trading system. The agent quickly learned patterns from the training data and improved performance through backtesting. However, certain areas like handling unfavorable position and incorporating additional data source require further exploration and improvement. The actor critic algorithm are currently considered highly efficient in reinforcement learning. However, rigorous and extensive training is necessary before deploying this model in real-world trading scenarios to ensure accuracy and effectiveness. Thank you for all your attention. I deeply appreciate this opportunity to share my research with you. Thank you.